Good morning. I will start the session 10A. My name is Jozef Ritonja. I'm coming from Slovenia, from University of Maribor, Faculty of Electrical Engineering and Computer Science. In this session, we will have contribution from the area of electrical engineering. There are 6 contributions. All presenters are here. It means we will start now at 9:30 and we will finish at 12. We will finish at 11, so every contributor will have approximately 15 minutes. So if it is possible, I ask you not to exceed the limitation. So if you agree, I suggest that we will start. Our first presenter will come from Poland, from Gdansk. This is the paper in the area of synchronous machine and control systems. The title of the paper is Improving Control Dynamics of Permanent Magnetic Synchronous Machine Drive. There are 3 authors, and the presenter is Mr. Leszek Jarzebowicz. Please.
Good morning to everyone. Thank you, Mr. Chairman, for introducing myself. There is a little mistake in conference program. Only the first part of the title is there, but the full title is Improving Control Dynamics of PMSM Drive by Estimating Zero Delay Current Value. Dynamic properties are crucial to many applications. In such cases, typically the solutions are fitted with PMSM motors due to their good dynamic performance. Moreover, we can distinguish different kinds of drives. Some are torque control, and their control algorithms consist only of one control loop. This is a current control loop. There are also speed or position control drives, which contains also outer control loops for controlling speed and position. However, in all those cases, the properties of the most inner control loop, that is current control loop, is ultimately limits the performance of outer loops. Therefore, the inner loop is considered as the most important. And although there are numerous papers on some sophisticated control algorithms involving some expert maths and so on, still typical PI controller is very highly appreciated in most of the solutions. So those facts motivated us to propose a solution which enhances the capabilities of typical PI controller by estimating motor current values for the beginning of the forthcoming control cycle. It's something connected to predictive control, but very simple predictive control. And this solution allows us to significantly increase dynamic properties of current control in PMSM drive. Here's a typical structure of field-oriented control applied to PMSM drive. Here's inverter, motor. Some values are measured by digital controllers. They are DC voltage, motor phase currents, and rotor position and speed. Phase currents are transformed into DQ coordinates in order to enable the controller to easily control motor's torque. So we have to control 2 current components. D component is usually forced to 0, and Q component is set accordingly to desired torque. And if we consider the fact that this algorithm is implemented in digital controller, we have to take into consideration that this algorithm operates on the basis of sample and held values, and it is able to update the PWM modulator only once per control cycle. So this somehow limits the performance of such algorithm in digital implementation. So here are some selected waveforms from such drive. At the bottom there is a PWM carrier, a triangle wave, which allows us to set the instance of inverter transistor switchings. In the middle with blue color there is a selected motor voltage, one of the three voltages. Voltages are modulated by inverter, so they change a couple times during control period, during control cycle, but the voltage is modulated in a way that its mean value equals reference value, so the one which is marked in green. And at the top there is a selected current waveform. Current waveforms, motor current waveforms consist of a significant ripple component caused by changes in supplying voltage, and the frequency of those ripples is much higher than control bandwidth. Therefore, control algorithms aims to control only so-called fundamental component of these currents, the one which is marked in green. So the controller needs to extract this fundamental component in order to provide current controllers with proper feedback. And a convenient solution to that was presented some years ago. It's called synchronous sampling, and it uses the fact that current instantaneous values, instantaneous waveform crosses the fundamental component line in the middle and at the beginning of control cycle. So if we sample current at those instants, we obtain fundamental current components. And if we consider some single control cycle, we need to set up a PWM generator before this cycle starts, so before this instant. So we cannot use this current sample to feed control algorithm because we wouldn't have any time to perform computations. So we have no choice, and we pick this or this sample as an input to control algorithm, and we update the PWM generator at this instance. So there is a delay between measurement and updating the generator. And this degrades the dynamic performance of such control loop. So the paper investigates how choosing the instant this or this influences control dynamics. Moreover, we propose to estimate the value at the end of the control cycle, this value, by measuring those two both values here. And we also investigate how such estimation, how such prediction influences control dynamics. So first approach was to perform some simulation. We've developed a model in MATLAB Simulink which represents all those digital phenomena, digital control phenomena, but there is no inverter in this model because we wanted it to represent only fundamental current component. No ripples are involved, and some outcomes are here. Here we have a triangle wave of PWM carrier and a step command, command of Q current component. This is torque producing component, and three responses to this command in blue, green and red color. The blue one represents the case when a current sampling is performed at the beginning of a control cycle. The green one represents the case of measuring the current in the middle of control cycles, and the red one is our proposed case of estimating so-called zero delay current value, so estimating the value at the end of analyzed control cycle. For each of those cases, controller gains were selected individually to obtain 5% gain to be able to compare those cases. And as you can see, by estimating zero current delay, we can effectively increase the response rate of drive. The rise time of this current is approximately 3 times shorter than the blue case and 5.5 shorter than the green case. So it is much faster than standard approaches. So we came to a conclusion: if our approach enables us to obtain such fast response, so we asked ourselves, is it possible to select such controller gain that will enable to obtain single control cycle response and simultaneously no overshoot? And we derived some equations which allowed us to take into consideration motor parameters and control cycle duration. I don't show you these equations here, but the paper is already published and available online, so I encourage you to look in the paper. But I show you only the results. Here is some tests for standstill, where the current changes after a comment, after a step comment changes from 0 to the rated value in a single control cycle. Here's a similar case, but it's on the move, so the rotor is moving with a speed of 25% of the rated value. So the voltage is needed to cancel EMF force, but still our advised gain allows the controller to achieve one control step long response. And the last case is a case of quite high speed. It's half of the rated value. In such a case, the voltage needed to force the current to change to the desired value is higher than inverter output maximal voltage, so it's limited. In such a case, it takes longer than one cycle to obtain the desired response, but it's still technically the shortest possible time to obtain this. And here are some experimental validation results, some oscilloscope recorded waveforms. The one at the top is the most important. It's the IQ current, so the current components which is connected to torque production. And 100 microseconds, it's the duration of control cycle in our case, in our laboratory stand. And 10 amps is the rated value. And following the step command, the IQ current follows the command in one cycle. So in one cycle, the current fundamental component marked in red changes from 0 to the rated value. So we achieved our goal. And some conclusions. Our solution is very simple to implement. It's only marginally increase the computational complexity of control algorithms. In our case, it takes only 6 clock cycles to estimate zero delay control value, so it is about 0.1% of total computation time to involve this upgrade in control system. Although it significantly improves control dynamics, so we have high gain with very insignificant effort. Our approach does not require any hardware changes, although it requires increasing current sampling frequency with a factor of 2, but it's easily achievable on modern digital signal processors. And this solution obtains allows the controller to achieve the fastest technically possible response over step command. And that's all. Thank you for your attention.
So thank you for your presentation. Questions?
Just one question. The sampling time of your control, it's 100 microseconds? Or?
Yes, we have 10 kilohertz modulation frequency. So we sample current, but we sample current twice in each period. So it's 20 kilohertz something.
Could you explain in short words your experimental system?
The
size of synchronous machine and equipment?
Our experimental system was of a power approximately equal to 2 kilowatts, and it was controlled by digital signal processor, 32-bit processor of Texas Instruments, fixed point, and what's to say more? And we had interior permanent magnet synchronous motor of such power rating.
Thank you. So our next presenter came from Pilsen, from University of West Bohemia, Mr. Jan Stepanek, and his contribution is in the area of traction of vehicle tractions.
Good morning, gentlemen. Thank you for my introducing German. My presentation is about cost-effective solution of input voltage stabilizer of auxiliary drive converters for traction vehicles. Now let me give you overview of the I'm going to talk about.
This one, yes.
The other way. It's backwards, forwards, and laser pointer.
Yeah, my presentation divided to these 5 parts: motivation, auxiliary drives, the new converter concept of voltage input stabilizer, hardware prototypes, and the end is conclusion. And this research has been motivated by our industrial partner with the aim of developing new generation of equipment for light traction vehicles. For our research has been main aim is these parts: high efficiency, high switching frequency for reducing size and weight for passive components. Output power for converter is 22 kilowatts. Operating voltage range is 400 volts to 950 volts for DC catenary. Lifetime F, of course, low cost. The auxiliary drive has great importance for vehicle safety. This block presents a simple topology providing a galvanic isolation between catenary and auxiliary drives. Potentials and importantly protect 2 passengers in these vehicles. This is galvanic isolation. This is battery charger for onboard battery. The auxiliary drives are integrated of part of light traction vehicle. They are mostly used for generating a standard power grid which supplies on board equipment on the top vehicle. This is box for auxiliary drives and traction converter. This is commonly used composed concept of auxiliary drive. This is block of input voltage stabilizer or connection to DC catenary voltage. This is old concept. My drawback is they're using 70-100 volts semiconductors with lower switching frequency, around 8 kHz, higher switching losses, and exactly higher price. Only advantages for this concept is one phase source inverter with 20-100 volts semiconductors. This is novel proposal converter concept of auxiliary drives. This would converter based on serial combination. Two bucks enable using 20,000 volts semiconductors. The input voltage stabilizer converter is supposed input to catenary voltage to e.g. 380 volts DC. Main benefits for this auxiliary drive is high efficiency, reliability, lifetime, low price, reduced size and weight passive components. Advantages for this topology is using 20 volt semiconductors in input voltage stabilizer, high switching frequency, elimination of passive components, size, lower switching losses, and low price. Disadvantages is serial connections of two input converters and higher number of semiconductors in input voltage stabilizer. This table comparison existing concept and new concept. It was a concept to reduce price by 13%. This is summarized. Size by 7% and weight by 15%. This is hardware prototype for new input voltage stabilizer. New input voltage stabilizer consists of two modules. In this figure is one module, is a 3D module from Altium Designer. This is basic parameters for input voltage stabilizer. This schematic is a power circuit for this prototype. This is one section and two sections. Each switch is composed of three parallel components, three IGBTs without anti-parallel diode and SIC anti-parallel diode. This is testing and measurement results. This is converter startup waveform, shows balancing without force ambivalence. This is force ambivalence. There is major ambivalence. It is caused by asymmetrical of both sections involving capacitors C1 and C2 parameters, maybe tuning gate, drive pulse, and other parasitic influences in transistors. This is shows from balancing capacitor with force ambivalence. Ambivalence is made by external resistors. The waveform confirms proper function of balancing controls algorithm of inverse converters. This is balancing states. This slide shows measurements in steady state condition. This is normal function mode. In this figures shows input voltage step change in this value to this value, and load step change from 5 kilowatts to 10 kilowatts. The attention was also paid to efficiency measurement, as the losses may limit practical applications to do on the unacceptable temperature rise of the discrete semiconductors device. In this figure illustrated the efficiency curve for the nominal voltage voltage in and efficiency of over 97% is kept with the output power 2 kilowatts up to approximately 20 kilowatts. This figure, the influences of input voltage stabilizer efficiency documented in this figure, which also validate the proper function of the converter over the whole voltage range. It confirms of domain of switching losses, conductive losses at the values decrease with increasing input voltage. This is dominant switching losses in this area. And conclusion, the results provide the employing the latest generation of semiconductors device in a cost-effective discrete package, also the design of an input voltage stabilizer converter with an output power of 22 kilowatts, the capability of reliable operation with the full range of catenary voltage fluctuation 4000 volt DC to 9050 volt DC, achievement switching frequency up to 13 kilohertz. Likewise promise the better passive component optimization in comparison with concept with 1700 volts devices. The overall efficiency of laboratory prototype, which varies between 97% and 98% under almost all input voltage and load condition, promise feasibility design for industrial application. The new input voltage stabilizer concept reduced price by 13%, size by 7%, and finally the weight by 15%. This is comparison for parts of auxiliary drive. Existing concept use IGBT transistors and 7 kilovolts and switching frequency of 7 kilohertz. New concept using IGBT transistor with blocking voltage 1.2 kilovolts and 13 kilohertz switching frequency.
Per presentation or questions?
Your solution is designated for trolley buses, yes?
Yes, for trolley buses or trams.
And it's rated for 22 kilowatts, yeah?
Yes, 22 kilowatts, and
My question is, what auxiliary load needs such high power? Is it air conditioning?
yes, maybe air conditioning or this vehicle is input voltage stabilizer using for source for battery charger and maybe air conditioning.
Mm-hmm. Okay, thank you.
Yes,
Let me ask you, there was table with prices of transistors and so on. There was the second IGBT, only $7 per age. Very
This is discrete module. This is discrete transistors, and this IGBT is a big module. Is half bridge on the package.
Later you can tell me where you buy it.
These transistors
Later, okay.
on the Geeky.
For this price, yes.
For this price.
More question? I have perhaps the most important question. You finished the prototype, but have you succeeded to sell this concept?
Now this prototype with
So
transistors is finished. This is module, and traction vehicle used module with SIC FAT from Infineon. This is.
Yes, but the question is, have you succeed to sell it to any company that they will use your concept?
Okay,
Please.
response. This development is for the Škoda electric company in Pilsen, and there is a three possible way of the converter. This is one way with discrete H3 IGBTs, and the Škoda company choose the next one solution, and it's now with a confidential.
Okay.
And this solution, it's very similar, but the Škoda company choose the silicon carbide solution.
Okay, this is also not so bad because you obtained money before the study. so thank you for So the next paper will be from the area of exchange you will be from the area of power systems, electrical machines, synchronous generators, power electronics, and control systems. So very multidisciplinary project, very multidisciplinary presentation. I will be the presenter, Jozef Ritonja from University of Maribor, from Slovenia. So if I would like to present the topic of the paper in one sentence is how to damp the oscillation of the synchronous generator connected to the grid. So I will speak about the synchronous generators, the conventional synchronous generators which are used in the power plants. These are synchronous generators with the nominal powers from 10 kilowatt until 2000 megawatts. This synchronous generator produce more than 99% of total electrical energy. And these synchronous generators are very non-linear dynamical systems with two inputs, so we need two additional devices for operating. One of the inputs is mechanical torque produced by turbine, water or steam turbine, and the second input is the rotor voltage to generate magnetic field in the synchronous machine, and this rotor voltage is produced by excitation system. So it is funny, but it is true. Even when we have both inputs constant, the variables of synchronous generators are rotating, and where we can see these oscillations. The variables are oscillated. We can see these oscillations in the rotor movement, so rotor speed and rotor angle are oscillated, in stator voltage and in the produced electrical power. So here are the results of the measurements on the real power plant. This is synchronous generator with 30 megavolt ampere nominal power. Here we can see rotor speed and electrical power. So in real condition, we can see that also in this case, by constant inputs, the electrical power oscillates with the amplitude plus minus 10%. So this is this figure once again, so we can see this oscillation better. And here is For the analysis of rotor speed, we can see that we have oscillation with a frequency approximately 2.1 Hertz. The most important question is always, is this problem important, or is this only the problem to write the papers or to finish the PhD? The answer is very short. Yes, it is really very important problem. What are the consequences of these oscillations? First, we have increased losses, we have shorter lifetime, we have reduced peak performances, but sometimes it is much more important than because of this oscillation, we have a lot of blackouts of power systems. So here is a list of some blackouts in last years. So what are the reasons that we have these oscillations now? Because we use synchronous generators already 120 years, but we can see these problems in last 20 years. So the main one, there are two reasons. First reason is that we have extremely changed constructions of synchronous generator because of cost optimization. We have smaller damping windings and reduced damping characteristics. And next reason for these oscillations is, for these blackouts, is that we have we connect many different power systems, and to connect them we need a lot of additional control systems, and these control systems are interacting between themselves and they produce additional oscillations. So which are the solution for this problem? Yes, we can build the same synchronous generator as 20 years ago, but this is not the most intelligent solution. The better solution is that we will develop a new additional control system which will be able to damp these oscillations. This control system is called power system stabilizer, shorter PSS, because this problem is so important. So we will expect that such power system stabilizers are already on the market. Such stabilizer can be a part of excitation system, either electronic circuit, or model, software model. Yes, we can buy excitation system from many producers which already are equipped with power system stabilizer, but now this almost, or the majority, or I can say all these power system stabilizers are very ineffective. So we last year we made an analysis of Slovenian power system. We analyzed the power system stabilizer. Slovenian power system is similar to the Lithuanian power system, and we have 65 generators. Only 36 generators are equipped with power system stabilizer, and only half of this stabilizer is working, is operating. The other half is turned off because they don't increase damping. Either they do nothing or they decrease damping in some situations. So what are the reasons that the installed stabilizer don't operate correctly? First reason is that when we buy excitation system with stabilizer, we have to tune the parameters, and it is very difficult, it is very time consuming, and therefore some operators use factory settings, and these factory settings enable damping for some synchronous generator, but not for all, and not in all operating points. And next reason is that all these commercial power system stabilizers are based on the old linear concept, which is not convenient for such systems, for such a non-linear system as a synchronous generator. So, next question: what the researchers do? Yes, they do a lot of things in this area, so we can find more thousand papers contribution about this on this problem. So all modern control theories were used for power system stabilize, their design, everything what is written in control journals. First short conclusion is that the most promising methods for stabilizer are adaptive control and robust methods. It is also very important that in last year we can see a considerable cooperation between three partners: industry, universities, researchers, and operating facilities. And what is for me the most important thing that suppose that in the next 5 to 10 years somebody will invent such concept for stabilizing this oscillation, which will be good enough, so which will damp enough, and which will be simple enough to be built in almost all new excitation system. So I can say the competition is open. There is no winner here. So until now. This is a short introduction, this is a motivation. I think this is a really important problem. I will be very glad if somebody of you will try to find something new on this in this area. So about our paper, so we try to develop a new power system stabilizer. The working in this area in the control system is always the same. First we have to find mathematical model, control plan, then we have to analyze it, then we have to check what is wrong with the conventional power system stabilizer, then we have to survive all advanced control concepts, then we have to develop our new control method, and then certainly simulation experimental results. So about the mathematical model, synchronous generator is connected to the network, synchronous generator, transmission line network. It is is a nonlinear system which is very similar to the mass spring system. The oscillation here are in the area from 0.5 till 2.5 Hertz. The modeling is well known. We use Park transformation. First we obtain seventh order nonlinear model. After then we have to reduce. This model is good for simulation, but is too complicated for control system design and synthesis. Therefore we simplify this model and we obtain simplified linearized model, which is good, which is good for description of the dynamic of synchronous generator in the equilibrium point for which this simplified linearized model was developed. So model is simple. We have two inputs, mechanical torque or power, excitation voltage, three state space variables, and outputs. The parameters which depends on the operating points are K1 till K6. So if we write this model for nominal operating points, we obtain one set of these parameters, but for all other operating points we obtain other parameters. Here is block diagram. It is third order system, so if we have three eigenvalues, two dominant conjugate complex and one trial. Here is the comparison between full order nonlinear model and linearized model. Especially in transient response, we can see that the both models give almost the same results. Here are some results to see the influence of the different inputs on the outputs. So first we change mechanical torque of the synchronous generator for 5% for 10 seconds, and after then we change second input, so this is rotor voltage, for 10% for 10 seconds. Here are the results. Electrical power, the changing in mechanical torque produce these large oscillations. You can see here power, rotor angle, rotor speed, but small influence, small impact to stator voltage. But on the other side, the change in the excitation voltage produce like impact on the stator voltage, but small impact to the mechanical variables and electrical power. So it is very important that this simplified model is used only for the equilibrium state. If we change our loading operating condition, also the parameters of the models are changed. So we can see here, this is one of the parameters, K5. If we change the P, active power, and reactive power of the synchronous generator, the value of parameters is changed significantly from positive to negative value. It is what is new in this paper. New is that it is if we can see this figure, there is no information for us. We can see that the parameters are changed, but we don't know what happened with the dynamics of the synchronous generator. Much better is to investigate what happened with the eigenvalues. So this eigenvalue here depend on the operating point. If synchronous generator is operating its nominal operating point or in some else. So this rectangular is this one here. So we can see if we have the constant reactive power, every curve corresponds to the constant reactive power, and if we change the active power, so from 0 until 120%, so also the eigenvalue here, this eigenvalue moves, and the damping characteristic and oscillations are changed considerably. So we can see we made such researches by more than 100 synchronous generator. Always we can see the same pattern, the same shape, and from this analysis we can find the region. So the borders of the region where are these conjugate complex eigenvalues, which are the most important for the information of our oscillations. We can see that the frequency of oscillation can be changed from approximately 3 till 18 radian per second, so it is for 0.5 till 2.5 hertz, and here is the damping. So the short conclusion is that we can see from this analysis that we have really a lot of oscillation, that we need stabilization system, and that the dynamics of the control plant is changeable significantly in the entire operating range. So what is here we can see the results with the conventional power system stabilizer, which are already used in the nowadays excitation systems. So these are the results when no power system stabilizer is used. So here is active power oscillations, rotor angle, terminal voltage. When we use conventional power system stabilizer and we determine the parameters for this operating point, this is for nominal operating point, and the parameter of stabilizer as determined for this nominal operating point, we obtain very good results. The damping is the oscillations are well damped. But if we use the same stabilizer in some other operating point, in this case we can see that this stabilizer has the damping of this stabilizer is very weakly, almost the same as without stabilizer. Use in the so-called self-tuning control. This is one of the adaptive control systems. Here is the block diagram of the proposed control system. So we start with synchronous generator. The basis is the conventional power system stabilizer structure. So we measure one of the variables in which we can see the oscillation, and controller generates additional signal to the excitation system. Addition to this is the conventional. In the conventional power system stabilizer, we use parameters for the controller which are fixed, but we added to this system 3 additional modules. First, plant identification. On the basis of input and output of this control plant, we obtain the structure and parameters of the mathematical model of control plants. On the basis of these parameters, we calculate the parameters for controller, and the decision mechanism here is used to decide what to do. So if decision mechanism see that something is wrong, that the oscillation occurs, the decision mechanism stop the working of this controller, it start the identification. When the identification is finished, then it calculate the parameters, and he change the parameters of the controller of this power system stabilizer. So the modules here are conventional. We can use here conventional recursive least square identification model. We used here state space controller, and so this model are nothing special. So we tested different algorithms, And here are some results. Here are some simulation results. For these are inputs, load variation. These are changing in loads, and this is a measurement noise by voltage, stator voltage. Without stabilizer, we obtain such rotor speed, so a lot of oscillation. But if we use this self-tuning stabilizer, we obtain in all operating range. So this is for nominal operating point, or this is for some other operating point, almost the same behavior. So rotor speed is changing approximately 10 times smaller as in the case without stabilizer, and this is the output from the stabilizer. So about the experiments, here is the we test this algorithm in our laboratory. We used this is synchronous generator, 15 kilovolt amperes large synchronous generator. Instead of turbine, we use 30 kilowatt AC motor with frequency converter, displace and excitation system, and by means of this AC motor we produce a lot of disturbances. We change the mechanical torque, and here are the results in operating point 5 kilowatt. We can see that the oscillations are always in the during all perturbation very well damped. So far some conclusions. Oscillation of synchronous generator are harmful and very dangerous problem. Conventional solution is not good enough. We think that adaptive and robust PSS are very perspective concepts. We propose in the paper the usage of the self-tuning controller, which is based on least square identification and LQ regulator. We obtain good results with this controller and simulation and experimental results. And what is the most important, this discussed problem is really up to date, and it is worth to take time and try to find something better in this area. So thank you for your attention. I was a little bit too long. Are there any questions? Yes, please.
So, if I understood correctly, not all the oscillations are dangerous. So, can you just briefly explain about those blackouts? What really happened in those cases?
There are two sources for blackouts. There are oscillation in the active power. So if the power from the synchronous generator, the power which is transmitted from synchronous generator to the power system, and other are oscillations in voltages. So the main, it is honestly to say, the main source for the blackouts are the oscillation in voltages. These oscillations are not connected to this one, but these oscillations are also small source for the blackouts. So this is a step beyond, but it is not the most important thing for the blackouts. But
okay.
it could be also the reason, it could be also source for the blackouts. And there are...
The source for instability.
Yes.
An overall system.
Yes, please.
Yes, at the beginning of your presentation you showed us results where the frequency of oscillation was approximately 2 Hz.
Yes.
And it was on high power generator,
Yes.
observed on high power. And on your laboratory test stand, the frequency is at the same level, or it shifted?
So I simplified a little bit this problem. So we have 4 types of frequencies. So the main problem by this instability, by this oscillation, are the frequencies. There are called the oscillations between synchronous generator and infinite bus. So we have also oscillation between different synchronous generator in the power plant, and the oscillation between some power systems, between areas. So I show only these oscillations. So, and the answer to the question, it is very difficult to say such a general remark if the generator is larger than the frequency are lower or something. So it depends, especially on on the connection from the synchronous generator to the power system. How weak is our transmission line? How strong is the transformer between? So in our case, in our laboratory case, we have frequency a little bit higher. So it was 2.1 in the real power plant by 13 megawatt, and by 15 kilowatt we have a little bit less than 3 hertz.
Thank you.
So thank you very much for the questions. So I will continue. So please. Next, our next presenter would like to introduce himself, Mr. Bedrich Bednar. Do this.
Thank you, Mr. Chairman.
Here is.
So let me first introduce myself. My name is Bedrich Bednar and I am a PhD student at the Faculty of Electrical Engineering at the University of West Bohemia in Pilsen, Czech Republic. I'm working at the Department of Electromechanics and Power Electronics, and I'm going to talk about one part of my dissertation, which topic is high voltage converter for electrical drives. Sorry. Just now I'm doing research into novel control strategy of single matrix traction converter with variable switching frequency. Now let me give you an overview of what I'm going to talk about. I will start with introduction of AC traction topologies. Then I will like to tell you something about single phase matrix converter and its commutation. After that I will speak about switching frequency of matrix converters. I will show you modular concept, and I will show you measurement on our laboratory model. Finally, at the end of my presentation, I will draw some conclusion. On this slide you can see two ways how the traction drive can be realized. There is classical AC traction vehicle topology with line traction transformer. This transformer is very bulky, and this is big advantage this topology. Next way how the traction drive can be realized is use medium frequency transformer. Using medium frequency transformer dramatically reduce weight of electrical equipment on vehicle on the railways. If we using medium frequency transformer, we have to use a high voltage converter and its filter. For using medium frequency transformer, we need to transform low AC traction frequency to higher. European trolley standard are 25 kilovolts per 50 hertz or 15 kilovolts per 16.7 hertz. On this slide you can see modern topology with medium frequency transformer. We use as high voltage converter, we use two matrix converters in serial connection. There are these capacitance create input filter and divide input high voltage. On this slide you can see only two levels of converters, but real application using 14 cells which use 6.5 kilovolt semiconductor elements on 25 kilovolt trolley. These schemes using sorry, never mind. Primary side of medium frequency transformer is using serial connection matrix converter, but secondary side on medium frequency transformer is similar to classic topology. On this slide you can see detail of single phase matrix converter. There is 4 switches. One switch is created from 2 semiconductor elements, 2 IGBT in anti-serial connection. For example, S0 and S1. Input terminals is source and output terminals is medium frequency transformer. They have to attention to forbidden state. There is short circuit of input phases and cut output phases is impossible to use. On the right side on this slide you can see switching combination. There is 4 states. S equal 1 means that source directs correctly to load. States S equals -1 is indirect connection between source and load, and 2 states S plus or minus 0 means that input terminals are disconnected and there is 0 input current. On this slide you can see 2 ways how the matrix converter can be will be commutated in. This is 4-step commutation, both examples. One commutation is using knowledge of input voltage polarity, and this is 4-step switching commutation, and at the bottom of this slide you can see time diagrams when show when the switches are open. Thick lines means open elements with current. A thin line means open elements without current. For positive current is the same switch combination as for negative current, but we can show different current with different current. Second way, second commutation is depend on knowledge of output current polarity. There is time diagrams too and switching combination. This is 4-step commutation too. On this slide you can see our combining commutation. There is section in section 2 and A. There is very small current, as you can see. Therefore, we should firstly commutate based on knowledge of voltage polarity. In section 4 and 6, there is low voltage, and we commutate by the knowledge of voltage polarity. In section 1, 3, 7, and 9, we can choose commutation based on knowledge voltage, input voltage, or input or current knowledge polarity. Problem is section 5. In section 5, polarity detection can be hazardous because both current and voltage are very small. On this slide you can see how frequency may affect to weight of transformer. There is marked 2 points. First point means using frequency, low frequency from trolley 16.7 Hz. There is very big weight of transformer iron core. If we use 400 Hz, the dramatically reduce weight of transformer, as you can see on this slide. We try optimization of switching frequency because constantly frequency isn't optimal because matrix converter has time variable magnitude of voltage. We can adjust actual value of switching frequency according to actual value output voltage to obtain maximal power with minimal switching frequency without saturation magnetic core. The Q means number of switching instances during one period of supply relay frequency. There is balancing input filter capacitors using magnetic core. On this slide is separate levels of drives, and each matrix converter has separate medium frequency transformer. There is no magnetic couple, and we have applied to special control algorithm for balancing input filter. On this slide you can see our measurement model. There is medium frequency transformer, input filter, matrix converter, voltage source active rectifier, and DSP in which our algorithm. On this slide you can see experimental results with using different Q. There you can see if we use odd number of Q and half period of output of voltage in medium frequency transformer starts with the negative polarity of voltage, and half period ends with opposite polarity of voltage. If we use even number of Q, there is negative voltage polarity, and half period ends with negative voltage polarity. This is an interesting result. I will draw some conclusion. Single matrix converter has been presented. Matrix converter commutation was described in detail. Switching frequency of matrix converter was discussed. Control strategy for for designing a traction converter for AC traction vehicles and modular topology was present. That means the new control strategy enabling extensive transformer weight reduction. Some experimental results are shown. Thank you for your attention. Now, if you have any questions.
Thank you, Mr. No questions? Please.
As I understood, you increase the frequency of the voltage by a factor of I don't know, 4, 6, 9, yes?
Frequency or Q, you mean?
I thought Q is a factor.
Q is using for optimization magnetic saturation of transformer. Frequency, switching frequency of medium frequency transformer, not good to use more than 400 Hz because there it creates some adverse states.
So my question is, what is the ratio of transformer weight with your solution?
The weight of the transformer in comparison with classic transformer 10 times change the weight of transformer if we use medium frequency transformer.
Thank you.
So,
Do you do this work with cooperation in?
This work is created in with our industry partner.
so thank you for the question, for the answers. So our next contribution is in the area of grid-connected inverter. The authors are coming from Technical University of Košice, from Faculty of Electrical Engineering and Informatics. There are two authors, Marek Pastor and Jaroslav Dudrik, and presenter will be Marek Pastor. Please.
Good morning, gentlemen. Thank you for introduction. The title of my paper is Predictive Control of Bit-Connected Multilevel Inverter with Output LCL Filter. The multilevel inverter isn't so important. It can be any type of inverter. The content of the presentation is some system model, then design of a predictive controller, Kalman observer, explanation why I need the Kalman, then some laboratory setup and measurements result which are not so satisfactory. The control system consists of LCL filter. There is an inverter. It can be any kind of inverter, not just a cascade inverter, and the system is connected to the grid. At first I need some dynamical model. If I want to use MPC control, I need state space model, so I created state space model. I have 6 state variables. The control system is designed in rotating reference frame. It means that I need DQ components, so I need to couple each current in DQ. There are 2 currents in the inverter side, in the grid side, and 2 voltages on a capacitor. There is a table with system parameters. The power is quite low, it's just 1.2 kilovolt amps, just for like laboratory verification. The switching frequency due to the multi-level inverter can be quite low, it's set to 5 kilohertz. There are values of the LCL filter, some resistance of, there are just parasitic resistances, and there are voltages of the cascade 8-bridge inverter. There were 3 8-bridge bridges with voltages of 160 and 30 volts. The idea of MPC control, the MPC controller is usually used for systems with either higher order dynamics or large time delays. The LCL filter is a system of 3rd order, so maybe the using of MPC controller can be beneficial for such a system. It was the motivation, how it will behave. Maybe you are familiar with MPC, I don't know, so I will just briefly explain it. I have some desired value which I want to achieve. Then there is some past inputs, and there is future control moves and the predicted states. The MPC controller chooses the best control move. It's based on some optimization criteria, and it tries to reach this desired value as soon as possible. There is a control horizon and prediction horizon. Prediction horizon is used to compute the future output of a system, and the control horizon is set to consider several control moves in front of, like in the future. To design the MPC controller, I need a prediction model. The prediction model is created from discrete model of a system which was shown on a previous slide. There are several matrices which just need to be calculated. There is nothing special about it, just some math. The cost function needs to be designed. This is a classical MPC control cost function where I have some optimization criteria, J. There is a free system response, Y. Then there are 2 matrices, Q and R, which are used to set up the MPC controller. The Q matrix is used to set the dynamic of MPC controller, and the R matrix is used to limit the dynamics of the output voltage. It means if I have some plant and I don't want to have abrupt changes in the control move, then I can set the matrix R and I can limit those. And if I want to have a precise tracking of my desired value, then I can set the Q matrix and I will optimize the controller in that way. To design the MPC controller, I need to calculate the control vector U on some prediction horizon and P. There are 2 matrices, M and G. Those matrices are calculated according to those equations. Those matrices come from this equation here. Just the first control move is applied on that UK, And to get that first control move, I need another two matrices, Kx and Kr, which are calculated according to this criterion. It's like math. There is nothing special about it because it's a classical MPC controller. Okay, that MPC controller was then applied to that inverter with LCL filter. Here is the structure of the control system. I have an inverter where I measure just the grid current. There are three variables, but I measure just one of them, and it's a grid current. The system is influenced by grid voltage. Then there is the sample and hold, or analog to digital converter. Transformation to alpha and beta, then to DQ. Then I have an MPC controller, but prior to MPC controller, I have a Kalman observer. That Kalman observer is used to extract the complete state of a system, because I measure just one state variables and I have three state variables and the LCL filter, so I needed to use the Kalman observer to measure the or to predict the remaining system states. The MPC controller, this block here has quite simple structure because there are just like two gains or two matrices and they are added together. There is some delay and then I get two voltages, UD and UQ, and those voltages are then transferred into alpha beta, and just the beta voltage is used for the inverter because it's only one phase system. Look at that Kalman observer. I think you are familiar with the Kalman observer. I have some dynamical process and then I have Kalman observer. That Kalman observer can do like two things. In this case, it can improve the information from a sensor because there is always some noise. So I can remove that noise from a sensor by using the sensor equations, and then I can predict or observe the system state if I'm missing some of the system variables. It was my case. I had only one measured system variable, and the remaining two, it means like inverter side current and capacitor voltage, were observed by Kalman observer. I had some laboratory setup. It's quite small system, so also the laboratory setup is quite small. There is RT lab to control the system. There is a cascade inverter, there is a grid and some measurements. Here you can see the parameters of the MPC controller. There is a mistake, I'm sorry. Which were used in this laboratory setup. The sampling period of a system was 200 microseconds. It was limited by the speed of my computer, which is quite old. So that's the system is sampled at 200 microseconds. The prediction horizon of the MPC controller was set to 10. The control horizon was set to 3, and you can see the values of matrices used for MPC controller and for Kalman observer. Okay, there are some measurement results, and it's like always, that's the biggest problem because you can see like two things here. The first one, the system or the LCL filter is undamped. It's like third order system which can oscillate, and there is no active or passive damping added to that system. Just the MPC controller used to damp the system, and you can see that there are two currents. It's ID current and IQ current. There is a reference, that the dashed line and the measured, and also the reference, dashed line, and those not nice measured results. So you can see that the system is stabilized because there are no oscillations. If I set some value of the current, then the system is stable. But the problem is that the system or the MPC controller needs the exact model of the system. And my model is consists of two things. The first thing is the physical model LCL filter. I know the exact parameters of those inductances and the capacitor value, but what influences the system is also the grid. And the grid has some inductance, which is in series with this LG inductance of the LCL filter. But that inductance was unknown for me. So the result of not considering the grid as a part of a system was that if I set some value of a current, then the controller isn't able to reach that value because the model of the grid is missing. So it's like the motivation for the next work. is to identify the grid inductance. The system is quite stable and it's operating in that small scale in the laboratory, but the main problem is that I didn't identify the inductance of a grid and it influences the model. So it's like the conclusion of my presentation. So thank you for your attention.
Thank you for your presentation. Please, questions?
Very common for dumping the noise or removing the noise doesn't always work. So how efficient was in your situation?
Well, I needed to tune those two matrices because one matrix can be calculated quite exactly because I can measure the noise from a sensor, but that the other matrix can be like just the try and error. So it was like quite good, but the main problem is that grid inductance. It's not known, and also it influences the Kalman filter because that Kalman filter uses the model of a system, and it also influences the MPC controller. So it's like two parts of a control system which are influenced by one unknown variable.
Yeah, to tune it.
Yeah.
Thank you.
And thank you for the answers. So our last presenter is coming from University of Ostrava. He's Mr. Václav Kolar. The title of the paper is Distributed Measurement System with GPS Synchronization and its use in electric traction. There are three authors, Roman Hrbac, Václav Kolar and Tomas Mlcak.
Thank you for introducing me. Let me present our paper. Our collective deals with measurement in power electric engineering, and usually measurement is distributed. That means we measure in several places which are distant each from other kilometer or several kilometers. This is one example. Another example, distances are also again kilometer or more. So we need to have some system which is able measure in different places simultaneously. For measurement we use this simple data recorders, computer, usually a laptop computer, and analog to digital converter. This is analog to digital converter by National Instruments, and it is equipped with simple voltage dividers and some overvoltage protection and low pass filters. And this is measuring software created in LabVIEW system. It's nothing special. But for distributed measurement, we need some time synchronization of these measurements. Because time accuracy of computer internal clock is not sufficient for our purposes. And for example, online data transfer, we reject it because it's not possible when measurements are several kilometers each from other. Sometimes it is in forest somewhere far from civilization. We experimented with radio time synchronization, but it was problematic. So at the end we decided to use GPS synchronization. Accuracy of GPS signal is very good, better than 1 microsecond, much more better than 1 microsecond. For our purposes we need accuracy about 100 microseconds. So we developed GPS time synchronizers, and we use one additional channel in our measurement system, and this channel measures timestamps from this GPS synchronizer. This is simplified diagram and photo of synchronizer. When we finish measurement, we have several data files, each from one measuring place, and in this software we put the data together. This green line is signal from GPS synchronizer. This is signal from another GPS synchronizer, and so on. And this software puts data together, and these pulses are used as a trigger for joining data together. But there is also a problem, because internal clock of analog to digital converter is not perfect. There are some small fluctuations in frequency, so sample rate of analog to digital converter is not always the same. The error is small, maybe 5 milliseconds per hour, maybe 10 or 20 milliseconds per hour, but sometimes we need to correct even this small error. The best solution of this problem is to use oscillator in analog to digital converter, which is tuned by GPS signal. This is possible, but very, very complicated. So we decided to use software solution. When here we have measured data, we do software resampling of this data. So and this software does also this resampling. So at the end we have one big data file from many measurement places as if it would be measured in one place in one computer. Here is one small example of measurement and measurement results. We measured in traction transformer substation which supplies railway traction 25 kilovolts, 50 hertz. We measured voltage and current here. We also measured voltage and current here on 1010 kilovolts, but now it's not important. And we measured also voltages in track relay substation. Track relay is a significant part of track circuit. Track circuit is circuit which checks if some segment of track is free or segment of track is occupied by train. These track relays worked with frequency 275 Hz. Distance between this transformer substation and track relay substation was about 1 kilometer. And here you can see example of results, and we can see that sometimes there is some interference between track current. This is traction current. This is 50 Hz current in traction line, and this blue voltage is voltage on primary coil of track relay, or opposite, sorry. This black is square voltage 275 Hz on primary coil of track relay, and blue one is voltage of second coil of track relay, and sometime amplitude of second voltage is lower or higher, and thanks to our synchronized measurement system, we found that this is because of interference between these peaks in track current and edge of this square voltage. This phenomenon isn't dangerous for train operations, but there is such phenomenon. It's here only as example of usage of our system. I tried to also make some simulation of this phenomenon, and simulation results of simulation are similar to our measurement results. So that's all. Thank you for your attention. Sorry for my English.
Thank you for your presentation.
Questions?
Fortunately, there are no questions. So we can finish our session just in time. So it's 10. And thank you for your attention, for your questions, and for your presentation. Thank you.